Yep. Thank you, Steve. So today's talk is about globular weak infinity groupoids. So last week, Mike gave a very nice tutorial on basically globular weak infinity groupoids. You have a lot of intuition and examples and so on. But he didn't give a precise definition. So the goal of today's talk is to give a definition. Well, to give a precise and concrete definition of globular weak infinity groupoids. So I will drop the adjective weak because everything will be weak anyway. So the original motivation is for homotopy type theory, for instance, constructing a model of the univalence axiom inside the type theory, or constructing a new type theory based on this idea. But for this talk, I will mainly take the point of view of just a classical mathematician who wants a definition of weak infinity groupoid, and I will give such a definition. So, so mainly we will work in ZFC, but everything I'm saying should be it should be possible to interpret this in type theory. There are a few technical issues, but it should be possible to do it in type theory. So we first recall the intuition of weak infinity groupoids and explain the idea of the definition. So what is an infinity groupoid? First, it's a globular set. So we have G0, which is a set of points. You see them at the objects of the infinity groupoid. Then, between any 2 points, you have arrows. So, given any 2 points x and y, you have a set of arrows from x to y. So, for now, it's just a graph. But then you have higher arrows. So, given any 2 parallel arrows, so if you have 2 arrows with the same source and same target, you will have 2-dimensional arrows. Well, several 2-dimensional arrows. Yes. Yes, because this is what globular means, basically. So there are several approaches to weak infinity groupoids involving different shapes. So here I'm using globular shapes. It means an arrow always goes from one arrow to another arrow, and the 2 are parallel. But you also have the simplicial approach, where you have simplices instead of globes, and the opetopic approach. We will have a talk tomorrow about opetops. So, and you have all the way up, you have between 2 parallel 2 cells, you have a set of 3 cells, and so on. So this structure is called the globular set. And then you will have various operations. For instance, you will have composition, identities, and so on. So to explain a bit the operation, I will adopt a type theoretic notation. So if I have an object of G, I will write it x colon G, just to remind of type theory. If you have P, which is an arrow between x and y, I will write P colon x equals y. If you have a 2-dimensional arrow between P and Q, I will write it alpha of type P equals Q in x equals y in G, and so on. So this is just a notation. This means P is an arrow from x to y. This means alpha is a 2-dimensional arrow from P and Q being both arrows from x to y, and so on. So, and you have a lot of structure on this. For instance, you have identities. if X is an object of the groupoid, you will have something IDX, which is an arrow from X to X. You will have inverses if you have 2 points. From X to Y, you will have some P minus 1 from Y to X. Then you will have composition. So if you have if you have 3 points X, Y, Z, and 2 arrows from an arrow from X to Y and from Y to Z, you will have P concatenate with Q of type X to Z. So for now, it looks like a category, but then you will have a coherence between these operations. So for instance, yep.
This structure that you're adding is not part of the globular set.
No, globular set is just a bunch of n-dimensional cells for all n, which are all built in parallel cells. Yes, and then an infinity groupoid will be a globular set together with all this structure. Okay. So, for instance, you want composition to be associative. So, if you have 3 arrows, then you will have some alpha PQR, which will be a 2-dimensional cell between the 2 composites. So it will be from P compose Q compose R equals P compose Q compose R in the type X equals T. But then if you have 4 composable arrows, then all the alphas can be put together. You will get a pentagon, the MacLane's pentagon, and then you will add a 3-dimensional cell, which will be a coherence. Then you also need coherence for inverses. That inverses should be inverses, but only in a weak sense. So, for instance, if you have a P from X to Y, then you want some kind of lambda P type P composed with, or P minus 1 composed with P should be equal to id of Y. So if you compose P with its an inverse that I have here, you get the identity. But again, this is a higher dimensional cell, and all the higher cells will interact with each other. So, okay. Yes, this is a lambda for left inverse. You can call it. You can do more. If you have two-dimensional cells like this, you can compose them. This is vertical composition. But you can also compose 2 cells horizontally. If you have 2 cells like this, you can compose them like that. And this arrow will be the composite of the 2 arrows up, and the arrow down will be the composite of the 2 down arrows. So this is horizontal composition, and then both will interact in that if you have a diagram like this, then you can either start by vertical composition and then horizontal composition, or start by horizontal composition and then vertical composition. You want the 2 to agree, but again, they will agree only up to a weak cell, to a 3-dimensional cell. And this 3-dimensional cell will need to satisfy some higher coherence, and will need to interact with the alphas and with the lambda and so on. So it looks very messy and very difficult to describe explicitly. But actually, something that has been noticed a few years ago, and which is the main reason for this special year, is that there is a setting where everything comes for free. If you're in type theory, and you interpret this as the identity type, then all this structure comes for free because of the J elimination rule. For instance, if you want to define composition, you say P is an equality between X and Y. I can destruct P, or induct on P. Then I can induct on Q. And then I just have to prove reflexivity. Same for associativity. You induct on P, then on Q, then on R. And what you have to prove is the equality between reflexivity and reflexivity. And this will be, again, reflexivity. And everything arbitrarily complicated that should be a congruence condition will be proven in the same way. We'll induct on every equality in the context, and then you will end up by reflexivity. So this is the idea of the definition. That the coherences of infinity groupoids are exactly what can be proved by an iterated application of J plus reflexivity in the end. Yes?
I have a doubt. You say exactly, but
Yes?
isn't it the case that identity types may be stronger than what you have here, than the group properties that you have here?
That you may prove more structure, you mean?
Yeah.
It may be possible, yes. But
From the perspective of type theorists, since it's supposed to represent equality, then it's much stronger than just having connectiveness by types.
yeah, but it's expected to be exactly a weak infinity groupoid. It has been proved that every type in Martin-Löf type theory has the structure of weak infinity groupoid, but and the other way around, it's supposed to be true. But
Doesn't the substitutional model tell you that type really doesn't
yeah.
have anything? What should
Yeah.
be there?
Yeah, there's a kind of complete
Okay.
result, yeah.
So you have a
Except-
answer for this.
Except that the relationship between the simplicial model and the globular infinity groupoid is not clear.
Okay.
Here,
Yep.
looking at the globular object as the globular object in set, and this is a collection of terms, or you're looking at it internally?
I'm working in ZFC. Here, so this is a globular set,
Okay.
and then this is just a notation to say this is an arrow from X to Z.
That's in set two.
Yes, but you can probably internalize it by having a globular type in the Martin-Löf type theory,
But that's
and then this will be
the point of view of take
no.
looking
I
at
will talk a bit about how to internalize it,
Okay.
but
okay.
you can just think of stat theory.
It's a little bit dangerous to write equals
Yeah.
when you're working in set.
Yeah.
In fact,
Equals with index. We
all
know.
all equals except for one have been indexed, so it shows that it's running again.
Yeah.
And the one that has not been is the lab.
Which one? Oh.
We know what it is.
Something like that.
I
Yep.
had a question. So isn't it possible to formulate some version of the J rule for a globular set and then say that a weak infinity groupoid is a globular set which satisfies?
Sorry, what did you say?
Is that what you said?
You have to have it with respect to vibrations, so you have to give that all issues.
Well, and just to repeat my question, I asked if it's possible to formulate a J rule for a globular set or some version of the J rule and then say that the weak infinity groupoid is a globular set which satisfies.
Well,
that kind of
every type is automatically a globular set if you equip it with the identity types. So The weakness, okay, there is a notion of a strict infinity groupoid. Is that you have identities, you have inverses at each dimension, you have various compositions in each dimension, but then associativity is a strict equality. And then inverses are strict inverses, the exchange rule is strict, and so on. And
Well, here they are
everything is up to a higher cell, and the higher cell must be coherent and so
I
on.
suggest we let Guillaume go on, because some of these questions he's going to answer as he goes.
Otherwise, we're going to run out of time.
Okay, so I will first start by explaining how to formalize the notion of global asset. So the usual definition is the following. You say that a global asset consists of a sequence of sets together with two maps source and target, which goes from Gn plus 1 to Gn. So Gn will be the set of all n-dimensional cells, and Sn and Tn will be the source and the target of this n-dimensional cell. And we need to express the fact that cells must be parallel. So for instance, here, if you take a two-dimensional cell, you take the source and then again the source. It should give the same thing as if you take the target and then the source. So you have the condition that the source, so the source of the source is equal to the source of the target, and the target of the target of the source is equal to the target of the target. So another way to say it is that you have a presheaf on some category G, which is basically the category generated by these equations in the other way around to get the presheaf. So this definition is a bit problematic if you want to internalize it in type theory, because you have equalities, and equalities are problematic because you would need also coherence between those equalities. So we will introduce another definition. So first, a little remark. If you have G a globular set, and if you have X and Y in G naught, so I will also write object of G to be sort of the object of G. Then there is some hom XY, which is a globular set. So there is, given any two objects, there is a globular set of morphism between the two objects. This is some definition. And that's easy to define. You say that an n-dimensional cell in the globular set of morphism between X and Y is an n plus 1 dimensional cell in G, such that the source and the target are X and Y. So the iterated source of sigma is X, and the iterated target of sigma is Y. So in particular, if you have a globular set, you have in particular a set of objects, and between any two objects, you have a globular set of morphisms. And actually, this can be taken as the definition of globular set. A globular set is given by the following. Globular set G is given by this. First, ob G a set. So you have a set of objects. And then for all X and Y objects of G, I want hom G X Y, a globular set. And you need to interpret this definition co-inductively, which means basically that so you need to give a set and a globular set of morphism between any two objects. And the definition, and this can be of infinite depth. You get some kind of tree, which can be infinite if you want. And there is a way to define things by co-induction. So, for instance, you can define the terminal globular set, which is the globular set with one cell in each dimension. Is defined by the following way. The object of the terminal globular set is just a point, just a single. You only have one object. And the morphisms between the point and itself is the terminal globular set. So co-induction allow you to make sense of this definition. So this may look circular, but it's not circular. Because basically you can unfold this terminal globular set, and you get that there is exactly one object, then there is exactly one morphism, then if you unfold it again, you get exactly two morphism, and so on. So, okay. And another example, if you take A, a type in Martinov type theory, then you can define some globular set associated to A. The object, so I call it A dot. The object of A dot are exactly the terms, the set of terms of type A. And the morphisms between two terms U and V are exactly the globular set corresponding to the identity type. So when I say A type in Martinov type theory, you can either you're working in set theory and you encode Martinov type theory in set theory, and then you get the set of all closed terms of type A. Or you can, if you work directly internally to type theory, you can just take a type, and what you will get is a globular type corresponding to A. So, and this definition of a globular set does not involve equality anymore. So if you want to internalize it, it will work very, very well, and it will give the correct notion of globular type. And if you see this as a dependent type over obj times obj, it will be exactly a redefibrant type. So it should be the correct notion. Okay. So I will not really use the co-inductive definition actually, but what I will use is that given any two objects, you have a globular set of morphism between the two. I'm not sure I will use the co-inductive property except for defining this kind of types. So now I can start to give the definition of weak infinity groupoids. So the idea is that I will define, it will be in two steps. I will first define some weak type theory, which will represent the internal language of weak infinity groupoids. And then I will say weak infinity groupoid is a globular set with an interpretation of this type theory. Okay. So we will define the internal language of infinity groupoids. Okay. So now I will define a type theory. The type theory will have 6 judgments. The first four are very classical. You have gamma is a valid context. Then a sequence of terms is a context morphism from gamma to theta. Then you have C is a type in the context gamma. And U is a term of type C in the context gamma. And then there will be two additional judgments. So there is no equality, no definitional equality. One judgment which says this pi theta dot C is a type of a coherence in a weak infinity groupoid. Is a type of an operation that should exist in a weak infinity groupoid. For instance, composition or the pentagon or everything. This is a context and this is a type. This is the type of an operation that should exist.
Do you mean that this is a type so that such that an operation of that sort should exist?
Yes.
Or this is just a type of the kind of thing that an operation could exist?
Should exist. This is the type of what should exist in every weak infinity groupoid. Yeah.
I don't understand the second line, John. Yeah, what does it mean?
This is a context. This is another context. And this is a sequence of terms.
Okay.
This just means basically that all the terms have the corresponding type in this context.
Okay.
I will give the typing rules. It's been yes. Yes. The substitution or context morphism.
It's kind of not a primary judgment, right? You can derive it from other judgments.
Yes, just as the gamma is a context, you can see it as a derived judgment or primary judgment.
From C's type and
Yeah. And there is another judgment, which is a context is contractible. And this is what will be needed to define what are the valid coherences. Okay, so we give the typing rules. Typing rules for context are the usual rules. The empty context is valid context. If C is a type in gamma, then gamma x colon C is a context when x is not in gamma. The empty sequence of terms is a context morphism from gamma to the empty context when gamma is a valid context. And then a context morphism from gamma to theta x colon C is exactly given by first a context morphism from gamma to theta, and then some u of type C, but with gamma substituted for, with gamma replaced by T bar, because it will be a dependent type theory, so this C can depend on theta.
Can you read the last line?
This one?
Yeah.
A context morphism from gamma to theta x colon C. Okay, so it's context morphism from gamma to theta, and then a term of type C, but dependent on the context morphism to theta.
What symbol you're using again? Before the theta?
Sorry?
Before the theta? Colon.
On the first premise, what is the subject?
T? The T?
The T.
T vector.
Yep.
Okay.
Okay.
It's tupling of terms and then substitution of tuples is here, right?
Yep. Yeah, this is just a sequence of terms, and you substitute
Substitute
everything. Substitute every variable in theta correspond to a term in T bar, and you substitute every such variable which appear in C by the corresponding term in T bar.
Telescope of terms it's sometimes called.
Yep.
So C is a theta type, but that's
Yes. C is a type in theta. Yes, maybe I should add. And x is not in theta. Okay, now the types. So there will be two basic types. There will be one type I call star, which corresponds basically to the ambient infinity groupoid. And there will be identity types. So if you have U of type C, and you have V of type C, then you have a type U equals V in C, which is a type. Okay, now the terms. So first you have the variables. So if gamma is a context, X is of type C as soon as X colon C belongs to gamma. And then the interesting bit, there will be a term corresponding to applying a coherence law to some terms. So if you have a valid coherence of type pi theta dot c, and in the context gamma you have basically something of type theta, so a sequence of terms of type theta, then you can apply it. So I introduce a new symbol, J, like this, which applied to T underline, which will be of type C, but of course with theta replaced by T underline. So if this judgment holds, then there is this special symbol which represents the coherence of this type. And I can apply it to any sequence of terms of type theta, and I get something of type C. Okay? No? If you have something like that, which represents a type of some operation which should exist in any infinity groupoid, then, for instance, yes, composition of morphism, which corresponds to such a thing, then there will be an operation like this, which has the correct type.
C is the correct type in theta.
Yes, this would be in this judgment.
Can you give an example?
Yep. So I have not defined this yet, but I can already give an example. If you take the following context, you have 2 points and an equality between them, and you take the type y equals x, which is a valid type in theta. So according to the rule I have not yet given, this is a valid coherence. And there will be some j pi theta dot c, which can be applied to any sequence of terms where this sequence of terms should be of type theta. So basically what it means is that if you can unfold the definition, and you see that if in gamma you have A and B 2 points and L a path between an arrow from A to B, then you can apply this to A, B, and L, and you get an arrow from B to A.
Well, a concrete example would be if you have a proof P x equals x, and you want to set the symmetric version of this proof,
Yep.
then you cannot apply J directly. So you can first do this and then instantiate.
Yes, you can instantiate with A and B being the same term. and given L of type x equals x, you get something else of type x equals x.
Yeah.
Yep.
So, but if you have J in specific instances of this rule,
I don't have J.
you don't
I have just this kind of weak version of J.
oh, so you don't. Okay,
No.
well, that means you have to add a number of axioms. Right?
Yes.
He doesn't.
Not.
But
I have not yet defined what does this mean.
this is just a thing called J. It's just a thing.
Yes.
It's not doing much.
Yeah.
Yeah, but then you have to specify.
We'll see as it goes on in the other rule.
I still have to specify somewhere. I have not defined what are the valid currencies. Yeah.
But I have a question just about what you've written. It looks as though you're substituting theta for t in C. That doesn't make sense. But t is a term of type theta.
T is of type theta, and C is in the context theta.
Yes,
So C contains variable in theta.
yes.
So and T gives you variables, the equivalent of variables in theta when you're in the context gamma.
Maybe it's an idea if you write down the type of the substitution operation.
So this brackets that you use, this brackets colon equals theta colon equals t means substitute the variables of theta for t.
Yeah.
So the variable.
The variables in theta, which appears in C, you replace them by the appropriate term in T bar.
Theta has variables and types in it. Ignore the types and replace the variables.
Okay? So, the valid currences, it's very easy. It's just, you want C to be a correct type in theta, and then you want theta to be a contractible context. And then we have enough. And then we just need to explain what are the contractible contexts. Contractible.
What is it?
Contractible.
Contractible.
So first rule, the context with exactly one point of type star is contractible. It corresponds to a point. And then, if you have theta a contractible context, and if you have an x colon c, which is in theta, so you have a contractible context, and you pick some variable in theta, then you can do the following. You have theta, you duplicate the x colon c to a y colon c, and you add an equality. And this context is contractible.
Can you reread this rule because they are the full rule. So theta is the
So if theta is a contractible context, and you have a variable in it, which has some type c, then you can duplicate x. So you have theta y colon c, and then you add z of type x equals y.
Exactly the kind of context that comes up in the usual table.
Yep. So,
Especially the
for instance, this context, how do I get it? I start with x colon star, then I duplicate x colon star, and I add an equality between x and y.
The operation of paths is contractible.
Yep.
How do you get composition of two paths into this kind of context? Let's give a totally different example. Is this all the axioms or are there more axioms that will be coming? Yeah.
No, that's all the axiom of the type series. So to get composition of path, you need to describe the following context. And it will be, you start with x colon star. So x, y, z, p, q. You duplicate it, get y colon star and p of type x equals y. And then you duplicate y, get z colon star and q of type y equals z. So this is a contractible context. And in this context, you can consider the type x equals z. This is a valid type in this context. So you get a j corresponding to the composition, which will take two composable arrows and give a composite arrow.
But you'll want to add the j to the contract. Well, suppose you want to write associative text.
Yep.
They just use one. Yeah.
So I need a context like this. So I can do it in the same way. I have x, y, p, z, q, and t, r. And then in this context, I just write the type p composed with q composed with r equals p composed with q composed with r, where this composition is some j something for this context. So I can write this. This is well typed. Hence, there is an operation of this type. In the
contractible context for an operation can only be built up using these rules of contractible context. So it will be very simple and can't contain complex terms. But then the right-hand side, the C, the target type of operation,
Yep.
that can contain complex things.
The C can be very complicated, can be this kind of thing, can contain a lot of other J's, but the context can only contain variables. Yep.
Can I just unwind your first example of composition? You're getting the actual composite, which goes from x to y. There's x to z. There's a term there, which is the j, is it right?
Yep.
And you get it from that j elimination. So as a premise, you first have to show that you have a valid context by your pi operation there. And to
A
get
contractible
that,
context.
you use the other rule. You use the other rule from contractibility.
You first need to prove that this is a contractible context.
Exactly. By this
So
one.
using the two rules.
In order to get that it's a valid composition
Yes.
shape.
Yes. So once you prove that this is a contractible context and this is a correct type in theta, then you get that this is a valid type for covariance. And then you are allowed to apply J.
And
Yep.
in order to prove the contractibility, you use your other
You use
construction
this.
principles. That's what you did here, where you doubled some of the things and put in a path. So
Yep.
there are 3 steps or so to get the. Got it.
I mean, every contractible context starts with x colon star.
I have a question. So basically, each one of your contexts corresponds to like a certain finite number of cells, right?
Yes.
So in types in this context correspond to different ways to compose these cells. So if I have a context, then types in this context are kind of different ways to compose this cell.
It can be a
Types are
statement
global
about
sets.
the cells, right?
The
Types are global sets.
types will correspond to global asset that you can talk about if you have a context. So you can always talk about the ambient global asset, and if you have 2 terms, you can talk the home global asset.
I mean, for example, in the empty context, you can do star, and then you can do, or like in the context x colon star, you can do things like x equals x and flexibility and so on.
Okay, so basically, you specify which, given a context means you specify which kind of cells you are talking about, and then the C is the statement
Yes.
that you're making about
Yes.
how those cells relate to each other.
In all the examples, the premises are the contractible context, and the conclusion is just the type we want to prove.
Right, but the globular set which you have will be always the path set, right? So it's between some composition.
Always the
Of
what?
cells.
Would be always the what?
But they don't have to be
And
a
the only globular
composition.
sets there are the path sets.
Look, you start with one globular set and just go down path somewhere. Or we said home set of the globular set you started with somewhere.
Okay.
Okay, I'm not sure.
So the contractibility rules say that you always add a point and an equality between this point and an existing point.
the point is of type C. It can be a higher dimensional cell. For instance, you can do a context like this.
Yeah, my mistake.
You
But
first
was
add the point.
an object that exists already, and
And an equality between the old one and the new one.
you cannot add any of them without the other.
No.
So maybe you're about to say this, but then can you do this relative to some signature and like define a globular set that way? You throw in constants of type star and maybe and path constants.
Your way of generating the free.
Yeah, right. Yeah.
Yeah, let's let him go on before we do that.
Okay.
The semantics.
One question.
Yeah.
So the rule for deriving coherences, valid coherences, is that something? I mean, can you argue for this rule in general? Like if you had more types surrounding your system, for example, the empty type. I don't know.
No. It's not really clear how to extend it to when you have different types and interact with each other. It's just the internal logic to one infinity groupoid. And okay. So this is the first half of the definition. Now we need to say what it means explicitly to interpret this operation in a global asset. So you take a global asset, an infinity groupoid structure on A is given by for every valid coherence like this, you want an operation on the global asset which has the correct type. So for every operation like this, I want some JA which will be of the following type. So I also need to define what is the interpretation, but intuitively you will have a definition of interpretation, and the interpretation of a context will be, for instance, a set. So which will be the set of corresponding things in the global asset A. And this will exactly mean that this JA has the correct type when seen in the global asset.
Are those various thetas different from each other?
Yeah, they all the same theta or capital?
No.
Thetas capital?
Yes, some theta is capital. This one is capital theta.
Bad choice.
Could you point to the capital ones or underline them or something? Good, thank you.
So in this contour, for every valid pi theta C, will this be over pi theta sub C that's valid in the interpretation, or that's valid in the sense of derivability in the reason?
It's valid in the sense of this system of derivability. The sentence.
So we're using the interpretation in a moment, but this quantification is still everything.
Yes. So, and I need to define the interpretation. So, if I have a context, the interpretation of a context will be a set. I will first write the type of the interpretation. What? This means is a set. If you want. So a context will be interpreted as a set. A type, this is a gamma. A type in the context gamma will be interpreted as a globular set for every element in the interpretation of gamma. Then a term of type C will be basically a section of the interpretation of the term. So for every small gamma in the interpretation of gamma, you will have an object of the interpretation of C applied to gamma. So you take an element in the interpretation of the context, apply it to the interpretation of the type C, it gives you a globular set, and take its set of objects. So a term is something like that. And a context morphism will just be interpreted as a map. Okay, and how does it work? The interpretation of the empty context will be the singleton. A singleton. The interpretation of a context gamma, comma x colon C would be the set of pairs of an element in the interpretation of gamma, an element in the interpretation of C. I don't know if I should write it, maybe. Well, I can run for the first two, maybe. So the interpretation of the empty context is a singleton, and the interpretation of gamma x colon C is the set of pairs gamma A where gamma is in the interpretation of gamma and A is an object of the interpretation of C at gamma. Then the interpretation of types.
Can you write bigger?
This one?
Generally write bigger.
What?
Can you in general write bigger?
Okay. So the empty context is interpreted as a singleton. And the context gamma x colon C is interpreted as the set of pairs gamma A, where gamma is in the interpretation of gamma, and A is an object of the interpretation of C applied to this gamma. So the interpretation of C depends on an element in the interpretation of gamma. This is a set.
Yeah, but that's the set of pairs.
Yes.
Is it a function or not? For
That-
each gamma you have just one?
It's a sigma
It's a
type.
context.
It's a sigma type, if you want. It's a set of pairs gamma A. It's a sigma.
So that gives you one example.
Yep. The interpretation of types. So the type star will be should be a globular set, and I will always interpret it as A, because terms of type star represent the object of A, basically. And the interpretation of of the type U equals V would be interpreted as the hom globular set. So interpretation of C at gamma is a globular set. Interpretation of U and V are two objects of this globular set. So you can take the hom globular set. U. Now, interpretation of terms. Well, where should I write it? Can write it here. So, the interpretation of a variable. So this should take an element in the interpretation of the context gamma and return something. So it will be some appropriate projection. Because this small gamma, given the interpretation of context, will be a tuple of length, the length of gamma. So you take the projection corresponding to x, to the projection of x in gamma.
What is gamma? I lost track. The small gamma.
The interpretation of a term should, given anything in the interpretation of the context gamma, give you an object of the type at this interpretation. So the small gamma is this one. And it will be a tuple of elements, and you take the correct one, it will be of this type. Okay. Now, we want to interpret a term of the form j pi theta dot c of t underline. And this will be interpreted easily. So this little gamma is of type interpretation of big gamma. Now, this is a context morphism from gamma to theta. So the interpretation of this t underline is a map from the interpretation of gamma to the interpretation of theta. So you can apply it to little gamma. And then you can just apply the JA, which is given by the structure of infinity groupoid, to this element.
Is the extended context under the first semantic bracket around the J? Yeah, that one. What's that say?
It's what is here? It's gamma and C, where theta had been replaced by T underline. Yep.
So this allows, so basically your structure has very many congruences, different types, right? It looks like all of these are the ones that should hold, but that's something that should probably be proven, right? I mean, do you have a proof, or like, how do you know that what you got is actually an infinity groupoid?
It's the right structure.
Yeah. and
Bec-
not
because
something which satisfies more congruences than we want.
Because this is exactly equivalent to Grothendieck's definition of weak infinity groupoid. I probably not have time to say that, I don't know. But it's, yes. It's
Why don't you go on, then we won't interrupt you and you'll get to what you want to say.
Yep.
And there's the kind of general background of the fact that there are lots of proposed definitions of infinity groupoid out there. This isn't a question of the one suggested definition of infinity groupoid that you should be comparing it against to make sure it's right. There are lots of existing definitions of weak omega groupoid, and some of them are known to be equivalent, some aren't. So the answer to the question is also
Next time,
how does this compare to them?
maybe it's better to have another lecture.
Another lecture so that he can finish what he wants to do.
Yeah, because
We can have more discussion now and then
Yeah.
let him go. How about let him go on Friday?
would you be okay to
Yeah.
give another talk? Because
That way we can have some,
yeah, it sounds
Sure.
really interesting. So I would
take
like
it
to
slow
look
and let
into
him go
more
on Friday
and,
to
Yep, no
continue?
problem.
Okay.
alert.
Yeah.
Listening to it.
Yeah.
One thing in particular, could you, so if you draw a 3 arrows on one of its sides and 2 arrows on another. So 3 arrows you can compose in 2 different ways. So you get actually, then you actually get 2 pentagons. And you need to fill it in with a 3-dimensional cell.
Yes. So in order to talk about the pentagon, you need to have you need to be in this context. You have 4 composable arrows, and then you write some complicated term corresponding to the pentagon. And then your 2 pentagon, you can write the 2 complicated term corresponding to the 2 pentagon. And in this context, state that they should be equal, and they will be equal.
Yeah. The reason I'm a little worried about 2 pentagons, when you write a pentagon, the sides of the pentagon are coming from the context, right?
Yes.
So these are compositions of things coming from the context. Okay, but the pentagon itself, you're also thinking of it as kind of a composition, high composition of the same things coming from the context.
Yes.
So if you want to prove that every coherence you have follows from the J rule, then you would go to the model and say that you said that it's the same as the Grothendieck one.
No, to prove that, so we can prove that a type in Martinov type theory is an infinity groupoid for this definition.
Yeah.
But this is, if you want, this is a special case of the J rule. If you want to prove this, by induction on the context, if you have a context of this form, then you can apply J to this path, and then get a smaller context. There is something to check when you arrive to the terminal context, that you can apply reflexivity. But basically, the idea will be that everything you can define has the property that when you apply it to only reflexivity term, it will definitionally reduce to reflexivity. So everything you can define will in this context, will be equal to reflexivity to the n of x.
To understand the structure of the C type, of the type C that you're stating?
The type are just identity types and one basic type.
Yeah, sure, but you have more types. Oh, okay, so you're not.
Okay.
In this
Type
theory,
theory.
just for the purpose
Of this definition, he's not making a new type theory. Is it done? Is that the end of the definition?
Yes.
Could you somehow show a secondary composition? Like, suppose you get a 2-cell. Well, just showing a 2-cell would be good. Could you show a 2-cell?
Yes. So if you want for this context,
No. I mean
Yep.
something like a pentagon, like a coherence 2-cell.
The interchange law, maybe something like that.
I can
Maybe interchange law.
write the interchange law.
Uh,
So to state the interchange law, we first need to define vertical composition and horizontal composition. So we introduce this context. So this can be written as the form of a contractible context. You have x, you duplicate x and add the path between x and y, and then you duplicate p as q and add the path between p and q, and duplicate q and add the path between q and r. And in this context, you have the type p equals r. So there is some appropriate j, which will be the vertical composition of alpha and beta. So this is contractible. So this is the theta of vertical composition. And in the context theta of vertical composition, the p equals r in x equals y is a valid type because the context contains p of type x equals y and r of type x equals y. So this is a type. U equals v is a type when u equals v in C is a type, when u and v are of type C in the context. Yep. This is just the identity types. And here in this context, P and R are both of type x equals y.
Okay.
So this is a valid type.
A valid type. Thank you.
So there is a J theta vertical composition P equals R of everything, so and alpha and beta, that you can write alpha star beta star 1 beta or something like that.
By contractibility.
Yes, because this is contractible, so you have such an operation.
And it's contractible because you built it up by the rules of contractibility.
Yes.
Wait, I have a question about the rules of contractibility then.
Yes.
So if your initial context has 2 points, how do you say that the paths between them are contractible?
But you can start with
The contractible context has not built 2 points.
A contractible context is just built in this way. A context with 2 points is not contractible.
Right, but the paths between them.
If you have 2 points and you add a path between them, it becomes contractible, but because you can apply the rules here.
But we don't ask about the context we don't ask about the home context between 2 points. Contractibility is there only defined on that context. And contexts are always closed.
Okay, I'll ask after.
Okay. So now we can define also horizontal composition. Yep. So this is a context. This is a contractible context because you start from x, you duplicate x into y and add the path between x and y, and you duplicate y and add the path, duplicate p and add the path, duplicate q and add the path. And then you consider the type p composed with q equals p prime composed with q prime. This is a valid type. So you get some alpha star not of beta, which will be of this type, which is the horizontal composition. And now, to get the exchange rule, it's again the same. Consider this context, alpha 1, alpha 2, beta 1, beta 2. This is a contractible context. Again, you can build it using the rules there. And in this context, you can state something like alpha 1, star 1, alpha 2, not beta 1, star 1, beta 2 equals whatever is needed, alpha 1, star not beta 1, alpha 2. So, yep. So this is well typed. You check that this is well typed, and there is a occurrence which has this type, because the context is contractible.
So BC you could also get by substituting into the ordinary composition, right? Like
Ordinary composition is defined for one-dimensional paths. And
We don't have dependent contexts, so
yeah.
vertical composition wouldn't be an instance of
Yeah. Okay, good.
It would be its own defined phenomenon.
If you have like a variable with a type.
So the difference with type theory is that you don't have the computation rule.
Yes. You don't have computation rules here. Yep.
Yes,
Yep.
maybe you should demonstrate it. This is surprising.
Oh yes. The reflexivity. You take
These are globular types.
the context with just 1 point. So theta equals this context, and C equals x equals x. This is a valid type in this context, and this context is contractible, and you get an operation which has this type, which is the identity. if you have a P composed with reflexivity or identity on X, this will be equal up to some two-dimensional cell to P. So
Is this the equality of your symbolic?
so this will be, there will be a two-dimensional cell which give the equality between this and that, but it's not a definitional equality or strict equality. It's all weak.
You don't even have definitional equality in
No.
your system.
But in terms of the model, it's not equality in this subordinate set of this structure.
Yeah.
On your model, but it's not.
It might be worth pointing out that there are some other funny-looking contractile contexts, right? Like they have a point with three morphisms going out of it to three different points.
Yeah. Yeah, you can define.
So for people familiar with Hastings diagrams, globular sets, these aren't just the normal
Yes.
Hastings diagram.
Okay. That was my question.
And here in this context, you can ask this X is equal to this Y, and basically it will compute the path going this way. And then you can prove, if you want, that the path going this way is exactly the ordinary composition of the opposite of this path with this one, because you just state it in the context and it works. Yes, up to a dimension.
And you cannot ask whether two paths are equal because they don't have the same type.
Yep.
Can you always associate a picture to a context?
Every two-dimensional context, yes, because the board is two-dimensional.
The picture on the blackboard was, in some sense, a globular object. Because each time you want to describe the context here, you draw a picture of a globular set. I mean, for example, the globular set there has 3 vertices and et cetera, right? So
But
can you always do that? Or?
every context can be obtained by, you start with a point and you glue balls along hemispheres. So at each time, here you start with a point, you glue a one disk along one of these boundary, then you glue a two-dimensional disk along this boundary, and so on.
I see. You glue a disk along a lower or an upper, so to speak.
Yes.
Lower or upper hemisphere.
Yes. Here it's just a lower sphere because I only ask X equals Y, but we could also ask for a reverse.
Can you draw a connected diagram which is not contractible?
Yes. Something like this. If you have a point and a path between X and X, then this is not contractible. You cannot obtain it in this way. And it should not.
Can you draw one without a cycle?
Yes? Can do a sphere.
No, not connected, I
Oh, so you can. No, that's not very good. Yes, you can just a context with 2 points.
Sure, that's it connected.
Two paths between them. So like the 2 points become positions.
You want to connect it, it's not contractible.
You can put 2 paths and then two-dimensional path. Yeah, like this. So you can X, Y of type star, P of type X equals Y, Q of type X equals Y. What?
That's fine.
This is a circle. And then if you want, you can add alpha, beta of type P equals Q. You get a sphere.
So you said that your definition is related to the one of Grothendieck?
Yep.
Do you want us to talk about that on Friday? Would that be a good topic?
Yes. Can talk about that and other stuff. Yeah.
That semiosis has shown that the features of Grothendieck is the same as Bretagne. The same as Bretagne?
Yep.
It's just a different